Okay, so welcome all. Again, we are continuing with the, like the preferences and utility structure. So just a quick recall of what we did previously. Remember what we did? Remember, I promised you that we will understand what lies behind this demand curve, right? And then you guys told me that, oh, hocam, what determines this demand curve? What lies behind this demand curve? And what was it? You said mostly, remember? You said, your taste, your preferences, your income, prices of other goods and such. So we said that first we will be actually dealing with these guys, right? So then we said that, okay, so but how to represent these, right, your tastes, right? How to represent the statement when you say that I prefer this to this, right? So, or I like this more than this. So we said that we can actually represent your preferences and tastes, right, via a preference relation. And remember, we said that this is a binary relation, right? A binary relation is a relationship which actually links two elements of a set. That's what we said. That was the formal definition. And then we said that this preference relation is actually should satisfy certain properties. Remember, what were those? Right. So we said that the first one was completeness, right? And then you said that, oh, hocam, there is reflexivity, right? And then what was the third one? Transitivity, right? So remember that these properties are actually, they kind of mean that, like you shouldn't be that crazy. You should be actually making some choices which are internally consistent, right? So basically that's what we said. If you need to explain it to your grandma, that's what you would say, right? And then we said that, but if on top of this, but remember we defined the preference relation, we defined, so this guy, remember, this wiggly greater than or equal to sign. And then actually we basically, we try to write everything in terms of this preference relation. We try to represent, using this guy. But you said that, hocam, it doesn't look very, nice. It seems a little bit complicated, right? It's too abstract. Then can't we have some, another way of representing these stuff where actually we have, we can deal with the numbers and functions, right? And then what did we say? So you can represent your taste and preferences, right, via preference relation. We said that. And then we said that, but if we would like to use numbers, right? So if I want to, let's say, suppose I have these bundles, right? So how are we reading this? Remember, x1 was? We said at least as good as, right? x2. And then how are you reading this? x2, the individual is indifferent between x2 and x3, right? And you could have something like this, right? These are all bundles. Remember, we said that it could be like behzatçı and 2 chocolates, and it could be, what was it? Muhteşem yüzü or pis yedili, right? Pis yedili and 5 chocolates, whatever, right? So we were comparing these bundles. And then you said that, well, hocam, we didn't like this wiggly thing too much, right? So why don't we operate in a world where we use numbers and functions, right? And then we said that, is it possible to assign these guys, right, some numbers? We said it's possible, but under, remember which condition? That we can actually, this preference relation can be actually also expressed using a utility function. When did we say we needed, remember we needed another property here. What did we say, right? So if your preference relation also satisfies continuity, right? Then we basically say, so let me put it here, right? So let's actually go here, right? Then we said that then we can say that you can actually have a continuous utility function, right? So we can represent using a continuous utility function, right? So this is basically, so we needed, remember, and continuity, if you wanted to explain it to your grandma, what would you say? What did it mean? It means that you make choices, right? So it means that, right, you don't, actually there are not many ups and downs, right? So you don't have many sudden reversals, you don't have sudden jumps, right? So basically that's what we said. So we said that instead of saying this, x1 is at least as good as x2, we can assign x1 some number, right, using a utility function. Let's say this is 50, and we can assign x2 another number, let's say 40, okay? And then now we're in the world where we use functions and where we use sort of, like numbers. And then we can express everything, right, like this. And then we said that, but do these numbers have any meaning? Whether it's 50, 40, right? So then you said that, Hocam, you should also give this one what? 40, right? So like u of x3 is 40, u of x4, I don't know what we said, but let's say 10, okay? So these are equal, and this is greater than or equal to, right? But then we actually said that, so this is the case, but do these numbers have any meaning? We said no, right? So we could have assigned, instead of this, I could have written 5. Instead of this, I could have written 4. Instead of this, I could have written 4. And here, I could have written 0.1, right? So we said what? What is key here? As long as the order is, right, preserved, then, we can just assign any numbers, right? So that's why we said that these utility actually rankings are ordinal rankings, okay? They're not cardinal, so we didn't. And then remember, we talked about whether we can make comparisons across individuals and such, okay? So this was basically kind of what we did. So let's also write down our utility function. So the utility function, I think we said before, but I can also specify it as x2, right? So we said that this is a function, right, which is going to assign every bundle a number, right? How much satisfaction, how much happiness you get from that. So we said that, so like x is an element of this, but we said that this x is, so for instance, this x could be Rn, right? So we said Rn plus. And then we actually said that this is, if it's Rn plus, so it has like, right, an n tuple. And then this is going to be, right, so this is what we said. And these all correspond to, right, it means that we have like a bundle of n goods, right? And then these all correspond to the quantity of that good, right? Quantity of x1, quantity of first good, quantity of the second good, quantity of the nth good, right? So this is basically what we said. So most of the time, you're going to see that we would be dealing with two goods case, and then you'll see that the n good extension will be very, like immediate. So it will be, once you understand the two good case, it would be very easy to extend it to the n good case, okay? So most of the time, you're going to see something like this. So x1, x2, or sometimes we're going to call it, good x, good y, and then most of the time we would be dealing utility functions where we have actually two goods, okay? So basically, those would be functions of two variables, okay? So most of the time. And then, remember, what did we say? We said there is something else. So we said that, so these guys are, so there is actually a, so let me put this here. So remember, we actually said that these guys are theirs, right? So we talked about some properties, right? The preference relation should satisfy. And then if we want a continuous utility function, it should also have continuity, right? But then, actually, we talked about another property, right? Another thing which might be true about your tastes and preferences. What was it? Right? So we said that there is this thing called, you might like more of, right, a good, and if you're not decreasing the amount of the other goods, as you get more and more of a good, you might like this better, right? And then we call this concept more is better. And remember, what did it mean? So more is better. Okay, what did it mean? It meant that, so we have, remember we said something, we have, so more is better, but we said that, so these guys are actually, right, x, y, or x1, x2, xn, they're all goods, right? So we said that they're literally goods, they're good for us. So that's why we want more of them, right? So we said that like more is better, it basically means that we have goods. Okay, not bads. So these are literally goods, right? So and remember we said that many of any good xi and no less of the others is actually preferred to less of xi and no less of the others, okay? So basically, so this is actually what we said. And then remember we said that suppose we have, so let's put this here. Suppose we put here the quantity of good x, right? And here suppose we put the quantity of good y. So this could be, let's say, you know, some drink here. Let's say it's Coke, beer, whatever. Okay, let's say here I have chips, pizza, okay? And then we said that suppose we have our bundle, x star, y star. And then you said that, oh, hocam, if we have goods, then we can actually divide, right, this quadrant into some regions. And you said that in this region, all the bundles are, what did we say? They're preferred to, right? So you said that this is actually better than x star, y star, right? Because, for instance, here you have more of x star and you have more of y star, right? So, and what about these guys? Here, do you think I should include them also in the better than set? Right? You said that, oh, hocam, because this has exactly the same amount of x star, and so this has exactly the same amount of y star, but now it has more x star, right? So if there is more is better, then individuals should be liking these guys more, right? So we can call this better than set. Okay, or preferred to, that's what we said. And then according to this, here in this region, we called it by a similar logic, right? So this is going to be the worse than set, right? So this is actually worse than set, right? So this is actually, so all these bundles, because they provide, you know, less of x star and, you know, like less of y star, or at least the same amount as y star, but less of x. So we called it worse than set, okay? But suppose, for instance, think of a case that my goods, so let's say, example, suppose I have goods like this. Here, instead of, for x, I said that this is crime. And for y, here I put pollution. And suppose this is x star, this is y star. Okay? Then do you think more is better is satisfied? Right? So do you like more crime and no less of pollution, right? You like that? No. Right? So what is it? So here you see that, so which part would be the better than set then? Here this region is still better than set? No, right? This is actually worse than, right? So you're having more crime and more pollution, right? So basically here is going to be better than set, right? So it would be completely the reverse, right? So you see that it's important how you know, like whether you're dealing with goods or bad. Yes?
But these situations are not good. We said goods more is better, but
for bad, more is not better, right? Yes. Yeah, so you see that it depends, right? It depends on type of goods. So this is basically, so just be careful. It might, or even if it's goods, right? Remember some of your friends, they were saying that, hocam, I cannot drink, you know, like 20 cups of coffee in a week or maybe in a you might drink in a week, but in a day, right? So it's so more is not always better, right? But you'll see that most of the time, so that things are moving nicely and you know, in a nice manner, we would be assuming more is better. But remember, always remind yourselves that that is an assumption and that's not necessarily true all the time, okay? So in which cases it might fail, in which cases, so you should always keep those in mind, okay? So just keep that in your mind. If we have bads, then this better than and worse than sets might change, okay? So now, but we said that, remember, we decided on the better than set and worse than set, but we said that, oh, what's happening here? What's happening here? Do we know? We don't know. For instance, if these are my grandmas, or you know, like I picked this example. I think these were the preferences of Harun. Again, the Besatçı character, right? So for your friends who doesn't know, so these would be the people in this course. So actually, these were his preferences, right? For you know, I think he has beer and chips, right? He was always eating chips and he was drinking beer. But so basically, but we have to ask that individual, right? We have to ask Harun or your grandma or you. So can you tell us the other bundles, right? Such that you're indifferent to X star, Y star. Just tell us those bundles, right? So suppose they tell you those bundles and then you connect them. And then this curve we called what? Indifference curve, right? So all these bundles would give the same amount of utility. So let's call it U bars, okay? And then they're all going to give the same amount of utility. The individual would be indifferent to X star, Y star. And you'll see that this indifference curve will be very helpful for us to, you know, like analyze stuff. And the reason is the following. Actually, if you think of the utility function, right? Suppose you have two goods. So the utility function, if I want to represent this, I want a graph of, you know, like dimension of what? If I need to show this. So I have, right, X, I have Y, and also I have the value of the function, right? It's like the utility level. So I need right? So it should be right? So it should be, the dimension should be 3, right? So basically, suppose, let's say that you have a cup, okay? And suppose you flip it, right? So like upside down, and you put it inside this classroom, okay? So this part is going to be like, you know, the X, and suppose that part is going to be Y, and then this is going to be the utility level, right? So if you have this much X, this was this much Y, this is going to be the utility level that you would get. You know what an indifference curve is? There's actually in math, there's another, you know, like a general name for this. These are level curves, okay? So for a utility level, let's say 5, I cut this function and I take that piece down to the XY plane, right? That is going to be my indifference curve, right? So it's going to be all the points which would give utility level 5, right? And which are actually projected onto the XY plane, okay? So we'll see, but just keep this in your mind that these indifference curves are actually what we call level curves, okay? So, so let's write this. Remember I told you that I was going to write down the formal definition. So let's say indifference curve. So indifference curve, okay? So basically, indifference curve is, we said that, you know, like it's going to give us the bundles to which individual is actually indifferent to. So let's actually, an indifference curve, okay? But what if we have 3 goods? Then what's going to happen? In order to represent the utility function, I need a 4-dimensional. Then this indifference thing is going to be what? Do you think it's going to be a curve? It's going to be, you know, I can slice it. It's going to be like, right, a curve that I actually projected into the XY plane. Now I have to project it on an XYZ plane, right, which is, right, it will be a surface, right? So that's why we can say that an indifference curve or an indifference surface, right, if you have higher dimension, okay, if we have n greater than 2, right, shows the set of consumption bundles, right, about which the individual is indifferent, about which the individual is indifferent. Okay? And then we actually said that that is bundles, the bundles all provide same level of utility. Okay? All provide same level of utility. Okay? So this is basically the case. So they're all providing the same level of utility, right? So this is what we mean by an indifference curve. Now, okay, so let me draw an indifference curve. And remember we said that this is how I draw the indifference curve, right? So, but just what do you observe? So you guys could tell me. So this is the indifference curve, right? That's what we said. So here I put here chips, here I put any Coke, beer, whatever drinks. And then I actually have this indifference curve. So we said that suppose this is going to give all the bundles, which would give the utility level U bar, right? So that's what we said. So we slice the utility function at, let's say, 5, and then we just wanted to trace out all the bundles, right? Which would give utility level 5. Fine, but if I draw the indifference curve like this, what do you observe here? There are actually two things that we could observe. So what would you say about for instance, the slope? Right, so slope, so like here, right, so let's actually consider this point. So let's say this has x1, this has y1, okay, so there's a bundle here. And let's say here I have x2, and here I have y2, okay? So slope at this point and slope at this point, what would you say? Is it positive? First, let's say, is it positive or negative slope? It's negative, right? What do you think if you need to explain it to your grandma? What would you say? What does it correspond to? The fact that slope is negative, what does it say? Huh? So it's actually, but again, grandma doesn't know convexity and such, right? So I'll define convexity, concavity, and everything today. But you see that slope is negative. So basically, what would you tell her is that, right? Oh, if you want to have, right? Like if I get some y from you, to keep you at the same utility level, I have to give you some extra x, right? So you see that there is some sort of, so this negative slope actually shows that there is actually a trade-off, right? In order to keep utility the same, if you want to have more x, then you need to give up some y, or if you're giving up some y, I have to give you some x, right? So that you would be on the same utility level. So the first thing that we observe is that this slope is, right, slope is negative. Right, so indifference curve is not something positively sloped, right? It's not that, like to keep you on the same utility level, I have to give you more y and I have to give you more x, right? Then it would violate what? Which assumption? More is better, right? If I had an indifference curve like this, then more is obviously not better, right? There are cases where you have more and you're completely indifferent, right? So basically, we said that the first thing is that slope is negative, okay? And then the second thing is that, but there is actually a special name for this slope. The slope of the indifference curve, so let me write it down, is given a special name, okay? Because it shows the rate at which you're willing to, right, give up y in order to have one more x, right? You can actually think of it like this. To have one more x, how many y's I'm willing to give up, okay? So this actually slope has a special name which we call marginal rate of substitution, right? Because basically it is showing right, the rate at which you're willing to substitute x, right, for y. So let me write that down. So that is going to be, again, you know, like we're defining stuff. So it's marginal rate of substitution. So let's call this marginal rate of substitution. Okay, so this is going to be, usually we actually say MRS, okay? So like, let's put it MRS of x for y, okay? So this is going to be basically slope of the indifference curve. But it's actually, so marginal rate of substitution is a concept that, you know, like, so we actually take the absolute value of the slope of the indifference curve because we know that this is negative, okay? So how can I write the slope of the indifference curve? If I want to write the slope of this curve, how would I write this in math terms? But that's, you know, like, bless you, that's sort of high school, right, slope. So like, right, so the more fancy way of writing slope, right? So it's, you can actually say dy, right, over dx, but don't forget that you're keeping along this curve, you keep the utility level constant, right, at u bar. But we know that this is negative. This number is negative. So like, we can actually put a minus here, okay? So this is basically MRS. You see that this is the rate at which you're actually willing to substitute x for y, right? So that's why it's called marginal rate of substitution. But it actually shows you, in order to have one more x, how many units of y you're willing to give up, right? So this is basically the definition. So you'll see that we're going to use this a lot. It will be very helpful. It will tell us a lot of stuff. But here, then you can actually say that when slope is negative, we said that this kind of shows the trade-off, right, between these goods. To stay on the same utility level, if you have less of one good, you should have more of the other goods, right? So that's actually basically showing the trade-off, right? So, and also there is, you guys were saying something else. So not only these slopes are negative, but there's actually another observation that we make. What is it? That's what's happening to these slopes. So the absolute value of these slopes, if you check, what's happening? So like, think of the absolute value. Here it's this much, but these get what? Steeper or flatter? Flatter. Right? So the slope is actually then getting, the absolute value of the slope is less and less, right? So what does that mean?
If you have more x.
Exactly, right? So then,
less relative y.
right? So exactly. So what does it say? That it says that, oh, so think of it like this. Suppose you had just, let's say, one Coke or like one beer, whatever, okay? And you had, let's say, 20 slices of pizza, okay? Then in order to have one more drink, you would be willing to give up, let's say, 5 pizzas or, you know, like, let's say 10 pizzas, right? So if you have just one drink and 20 slices of pizza, you would be willing to give up lots of pizzas to get another drink, right? But suppose you have 20 you know, like drinks, right? So you have like 20 cans of Coke and just 2 slices of pizza. In order to get one more, or let's say 5 slices of pizza, in order to get one more drink, how many slices of pizza you would be willing to give up? Like, again, 10, or it would be much less, right? Because you see that it's actually, these slopes are, as you said, that, you know, this marginal rate of substitution is actually decreasing, okay? So that is another thing that we see, okay? So slope, the absolute value of the slope decreases as x increases, okay? So this is what we said. The more, you know, x you have, then in order to have one more x, the amount of y you would be willing to give up would be less and less, right? The more x you have. So basically, this is actually the case. So you see that, for instance, here, indifference curve is more steep. It's actually steeper, but here it's flatter, right? So at this point, in order to have one more x, you're willing to give up less y compared to this case, right? So if you need to tell this to your grandma, what's going on with the slopes, you see that there is some sort of an economic intuition to that, right? Economic meaning to that, okay? So this is basically what we see. And this is actually called slope decreases as x increases. This is actually called diminishing marginal rate of substitution, okay? Diminishing marginal rate of substitution. And you know what? This diminishing marginal rate of substitution, some of you might say that, hocam, you have these guys, you know, like for instance, you have this guy because this indifference curve is what? There's a name for this, right, in math. It is convex, right? But is it just convex, or this is actually a little bit more than convex? It's strictly convex, right? So just always keep in your mind that, for instance, this is also convex. So I put here yx. So this linear, do we have diminishing, suppose my indifference curve is like this, okay? U is equal to u bar. Do I have diminishing marginal rate of substitution here? You say that, oh, hocam, what was diminishing marginal rate of substitution? It's the slope of the indifference curve, right? The absolute value of the slope of the indifference curve. But here, what is it? Does it change? It's constant, right? So is it diminishing? No. So this is, you see that, so here we have actually, so this concept is related to the strict convexity of the indifference curve, okay? So you see that there is, if you need to explain strict convexity of indifference curves to your grandma, you know what you would say. Oh, it means that the more x you have, you know, like in order to have one more x, you would be willing to give up less and less y, right? The more x you have. So basically, so this is actually a related to, as we said, strict convexity of the indifference curve, okay? So let's see this. So I will define convexity and concavity and such, you'll see. But before, let's actually do something else. Now, but this indifference curve, I draw it for a utility level, u bar. But there are other utility levels, right? So how will I show them? So suppose I put this. So let's say I put my indifference, so this is good y, this is good x, right? I put my indifference curve, u is equal to, let's say, u0 level, okay? And then there is also, let's say this is 5, right? There is also 6. So if utility level is 6, where do you think that indifference curve lie? Here or here? If it's more, it should be above, right? Somewhere. So this is going to be u equals to u1. Suppose u1 is greater than u0, right? So this way, I put u2. So this is basically, so what does it mean, right? In this direction, utility increases, right? So if you go in this direction. So we know that this happens when you like more, right? So it's when we have goods, you can say that, oh, hocam, this happens when we actually have more is better there, right? Because remember, if it were bads, then these utility levels should be increasing in which direction? This direction, right? So this is actually, you see that this is an indifference curve, just to give you definitions. And this is actually an indifference map. Okay? So it shows, all the level curves. So basically, so here, where the utility level is u0, u1, u2, right? So it's going to be, but this happens, this is not always the case, but if it happens, we know that there is more is better, right? So this is indifference map, okay? But when I draw these indifference curves, why did I draw them in a parallel fashion? Why didn't I draw them like this? So this is y, this is x, okay? So by the way, whenever you draw a graph, don't forget to label your axes, okay? Always, so otherwise they don't mean anything, right? So why didn't I draw them like this? So, right? So let's say this is u equals to u0, this is u equals to u1. u1 is greater than u0, let's say. Why didn't I draw them like this? Why did I draw them in a parallel fashion? So let's try to see. Now we're going to make our first proof, okay, in this course. So you guys might have some idea of what's going on, okay? But basically, so let's try to see. So let me ask this question. So let's write this, and then we'll give a break, okay? Now, here is the question. Can indifference curves intersect on such a map? Okay? So this is the question. Can indifference curves intersect? Okay, on such a map. So let's see, right? So let's try to see what's, if they intersect, what's going to happen. So let me actually draw this. So let me have a case where they intersect, okay? And let me put some bundles on this. Let me put A, let me call this B, okay? And let me call this C here. So let's call this U2, U1. And let's say that, suppose U2 is greater than U1. This is without loss of generality. You could have done it the other way around too, okay? So suppose U2 is greater than U1. Okay, so basically bundles on U2, right? It means that bundles on U2, the indifference curve U2, provide more utility than bundles on U1. Okay, so fine. So, but what can we actually say? Because A and B are both on the indifference curve U1, what can I say about A and B? They are, right? So we can actually say that, well, from here, A is indifferent to B, right? So we know that A is indifferent to B. And what can I say about B and C? They're on the same indifference curve, which is U2. Right, so this is also, so you can actually say that B is indifferent to C, right? So B is indifferent to C. Then what can we say? We have a property, right? If A is indifferent to B, B is indifferent to C, then what can we say? Right, so we actually, from here, we say that, right, because if there is transitivity, so let's say by transitivity, okay, we said that A should be indifferent to C, okay? But let's see what's going on here. But, okay, so let's see. Well, we know that A and B, they are on the same indifference curve, so therefore they should provide the same utility level, right? So let's actually put this. So let's say that since A is on, so let's say U1, or we can actually say it, and C is on U2, and we know that and U2 is greater than U1, what can we say? Right, we know that because A is on U1, C is on U2, right? And we know that U2 is greater than U1. Then? Right, so it should be the case that C is giving more utility, right? So C should be, so then C should be preferred to, right? A. Uh-oh, what's going on? We said that they should be indifferent, right? And here we said C should be preferred to A. So what do we call this situation? It's called a contradiction, okay? So you see that when you are trying to show stuff, you just, you didn't impose anything else, but you found two contradicting things, right? So this is a contradiction. So therefore, if you have transitivity, right, either you should violate transitivity, okay? But if you have transitivity, then you see that indifference curves, do you think they can intersect? No, right? You see that transitivity guarantees that they don't intersect, okay? So this is, then C is actually preferred to A. So let's say that here we have a contradiction. Okay? Sometimes we show it like this, okay? So this is actually, there is a contradiction, therefore they cannot intersect, okay? So let's put it here. Therefore, okay, indifference curves cannot intersect. Okay? So basically, apparently they cannot intersect, so I cannot have a map like this. This is out of question, so good. You see that we're in this nice world, okay? So this is, you see that this is a very simple, but it is, you know, like it's a proof. So we prove that indifference curves cannot intersect, okay? Now let's stop here, let's give a break, and then in the second hour we'll continue, okay?